Good afternoon, everyone. Today I'll be presenting the paper titled BigMap Future Proofing Fuzzers with Efficient Large Maps. This paper focuses on coverage guided fuzzing, which is one of the most successful automated techniques for discovering software vulnerabilities. Before diving in, here's a quick overview of how this presentation is structured. First, I'll briefly review how coverage-guided fuzzing works and how AFL's bitmap design operates. Then I'll explain the core problem, hash collisions, and why simply increasing the bitmap size does not solve it. After that, I'll introduce BigMap's key insight and walk through its two-level bitmap design. Then we'll examine why this redesign improves cache efficiency and overall performance. Finally, I'll go over the experimental results and discuss the broader implications for fuzzing research. As a little introduction, modern fuzzers like AFL and libfuzzer have found tens of thousands of real-world bugs, and they work by generating mutated inputs and using coverage feedback to decide which inputs are worth keeping. At the center of this process is something called a coverage map, which tracks which parts of a program have been executed. However, there is a major issue with how coverage maps are implemented in many fuzzers today. Because the map has a fixed size, edges in the program are hashed into it. As programs grow larger, this causes hash collisions where multiple edges map to the same location. These collisions reduce the fuzzer's ability to distinguish new program behavior, which directly hurts bug discovery. A natural solution would be to simply increase the size of coverage map, but doing that introduces severe performance overhead and dramatically slows fuzzing down. So we have a trade-off. Small maps are fast but inaccurate, large maps are accurate but slow. This paper proposes BigMap, a new design that removes this trade-off. It allows fuzzers to use very large coverage maps efficiently without sacrificing performance. In this presentation, I'll explain the problems more in detail, walk through the BigMap design, and discuss the experimental results that show why this approach works. To understand the problem BigMap is solving, first we need to know how coverage-guided fuzzing works. I'll use AFL as the main example, since BigMap is built on top of it. Coverage-guided fuzzers operate in a loop. They start with an initial set of seed inputs, then these seed inputs might be valid files, network messages, or any structured input the program accepts. The fuzzer then mutates these seeds, then these mutations can include things like flipping bits, inserting random bytes, deleting chunks, or splicing inputs together. After mutation, the program is executed with the new input. During execution, the fuzzer records which parts of the program were exercised. This is what's called coverage measurement. Once the execution finishes, the fuzzer asks a simple question: did this input explore something new? If the answer is yes, the input is kept and added to the seed pool. If it's not, then it is discarded. This process repeats continuously, sometimes millions of times per second. The important thing is to understand that coverage is the fitness signal. The fuzzer is essentially evolving inputs based on which ones can increase code coverage. If the coverage feedback is inaccurate or slow, the entire fuzzing process becomes less effective. And this is exactly where the coverage bitmap design becomes critical. Now that we understand how coverage guided fuzzing works, let's look at how AFL actually stores and tracks coverage. Now let's look at how AFL actually tracks coverage internally. AFL uses a fixed size bitmap, which is usually 64 kilobytes. This bitmap is essentially an array of bytes. Each time an edge in the program executes, AFL computes a hash value for that edge and uses it as an index into the bitmap. Then the byte at that location is incriminated. So each byte roughly corresponds to a program edge, although because hashing is involved, that mapping is not guaranteed to be unique. During execution, the bitmap gets updated dynamically as edges are encountered, but the bitmap isn't just written to. For every test case, AFL performs several operations on it. First, before execution, the bitmap is reset to 0. Second, during execution, the edge hit counts are recorded. After execution, the hit counts are classified into buckets. Instead of keeping exact counts, AFL groups counts into ranges like 1, 2, 3, 4 to 7, and so on. This helps reduce sensitivity to minor differences in loop counts. Finally, the bitmap is compared against a global coverage map to determine whether the input exercised any new behavior. If it did, the input is saved. If not, it's discarded. On this slide, as you can see how edges update different positions in the bitmap, notice how the updates are scattered across the array. This randomness is a direct result of hashing. The key takeaway here is that this bitmap is accessed extremely frequently. It is cleared, updated, classified, and compared to every test case. This makes it one of the most performance critical data structures in the entire fuzzer. And because it has a fixed size and relies on hashing, it is also where hash collisions occur, which we'll examine next. Now that we understand how AFL stores coverage, let's examine what happens when multiple edges map to the same location. Hash collisions are the main problem in modern coverage-guided fuzzers. Because the coverage bitmap has a fixed size, edges are hashed into it. This means that multiple distinct edges can map into the same location in the bitmap. When that happens, we call it a hash collision. At first glance, this might not seem like a major issue, but as programs grow larger, the number of edges increases significantly. Real-world applications can easily contain tens of thousands or even hundreds of thousands of edges. Meanwhile, AFL's default bitmap only has 65,536 slots. Even if edges were distributed perfectly uniformly, we would quickly start seeing collisions. And in practice, collision rates of 30 to 50% are common. This means that a large fraction of edges are sharing bitmap locations. Now here's why that matters. If two different edges map to the same byte, the fuzzer cannot distinguish them. So if a new input exercises a genuinely new edge, but that edge collides with an existing one, the fuzzer may believe nothing new happened. As a result, that input could be discarded. This directly reduces exploration and bug discovery. The situation becomes even worse when we use more advanced coverage metrics. For example, context sensitive coverage, path based metrics, or n-gram coverage dramatically increased the number of identifiers being hashed. That increases pressure on the bitmap and raises collision rates even further. So collisions are not just a theoretical artifact, they actively reduce fuzzing accuracy. Given that collisions are the issue, the natural instinct is to increase the bitmap size, and mathematically that works. Collision probability decreases as the map grows, but in practice, this solution introduces a more serious problem. And that's exactly what the authors examine next. So now we'll look into why simply increasing the bitmap size turns out to be much more expensive than it seems. At this point, the natural solution seems straightforward. If collisions are caused by limited space, we can simply increase the size of the coverage bitmap. A larger map reduces the probability that two edges will hash to the same location, and mathematically, this does work. Collision rates drop as the bitmap grows. However, in practice, this approach fails horribly. The reason that AFL performs multiple operations over the entire bitmap for every single test case. Before execution, the bitmap is cleared. After execution, it is classified. Then it is compared to a global coverage map. All of these operations iterate over the full bitmap size. So even if only a small fraction of entries were actually used during execution, the entire bitmap must be scanned. So when we increase the bitmap size from 64 kilobytes to 2 megabytes or 8 megabytes, we are dramatically increasing the amount of memory touched per test case. This creates two major problems. First, the cost of iterating over the bitmap begins to dominate runtime. Second, the large bitmap causes severe cache pollution. This processor repeatedly loads and writes memory that contains mostly zeros. This pushes useful data out of the cache and increases memory traffic. In the paper's experiments, this leads to a dramatic drop in throughput. With the default 64 kilobyte map, AFL achieves roughly 4,400 executions per second. When the map is increased to 8 megabytes, throughput drops to around 125 executions per second. That is more than a 30-fold slowdown. At that point, fuzzing becomes inefficient and impractical. So now we have a clear trade-off. Small maps are fast but inaccurate due to collisions. Large maps are accurate but extremely slow. This is the core tension that BigMap is designed to resolve. So the real question becomes, is the problem truly the map size, or is it how we operate on the map? At this point, the authors make a crucial observation. The real problem is not that the coverage maps are large. The real problem is that AFL operates on the entire map, even though most of it is unused. In practice, during a single fuzzing run, only a small fraction of possible edges are ever discovered. That means only a small fraction of the bitmap actually contains meaningful data. However, AFL's reset, classify, and compare operations always iterate over the full map size, so the runtime of these operations depend on the total bitmap size, not on how much of the bitmap is actually being used. This is completely inefficient. Ideally, the cost of bitmap operations should depend on the number of discovered edges, not on the maximum possible map size. BigMap's key idea is to separate where edges are hashed from where coverage data is stored. By doing this, it allows the coverage data to be compact and dense, even if the underlying map size is very large. This change removes the artificial dependency between the performance and bitmap size, and this is the core idea behind the two-level bitmap design. This figure shows the runtime breakdown as bitmap size increases. With the 64 kilobyte map, execution time dominates, but as we increase the map size to 2 megabytes and 8 megabytes, the time spent in map operations, reset, classify, compare, and hashing becomes the dominant cost. Notice that the execution time does not increase significantly. Instead, the overhead becomes the comes from repeatedly scanning the entire bitmap. This shows that the performance bottleneck is not program execution. It is operating on large, mostly unused coverage maps. And this observation motivates BigMap's redesign. So how exactly does BigMap redesign the coverage structure to achieve this? To solve the inefficiency of scanning large unused bitmaps, BigMap introduces a two-level bitmap design. Instead of storing coverage data directly at the hash location, BigMap separates the process into two structures. The first structure is called the index bitmap. This bitmap has the same size as AFL's original map. It maps edge identifiers to compact indices, and the second structure is the coverage bitmap. This bitmap stores hit counts densely and contiguously. Finally, BigMap maintains a counter called used key, which tracks how many entries in the coverage bitmap are currently active. Let's walk through how an edge is recorded. First, just like in AFL, an edge ID is computed. Then BitMap looks up that edge ID in the index bitmap. If this is the first time the edge has been seen, the index bitmap entry is uninitialized. In that case, the edge is assigned the next available compact index, which is equal to the current value of used key. Then, used key is incremented. After that, the coverage bitmap is updated at this compact index. From that point on, every time that edge executes, it will update the same compact location in the coverage bitmap. Now look at the figure on the slide. At the top, we see AFL's design. Each edge directly modifies a large sparse array. Then hit counts are scattered across the entire bitmap. At the bottom, we see BigMap's design. Instead of scattering updates, BigMap assigns each edge a compact slot. The coverage data is packed into the first few entries of the coverage bitmap. The rest of the bitmap remains untouched. This means that reset, classification, comparison, and hashing only need to operate over the range from 0 to used key. In other words, BigMap's runtime now depends on how many edges have actually been discovered, not on the maximum map size. Even if map size is several megabytes, if only a few thousand edges are active, only those entries are processed. This is the fundamental improvement. By introducing one extra level of indirection, BigMap transforms a sparse, cache-unfriendly structure into a dense, cache-friendly one, and this allows larger maps to be used efficiently. So now that we understand how BigMap reorganizes the bitmap, the next question is, why does this dramatically improve performance at the hardware level? So why BigMap is efficient? The main reason is improved memory behavior. In AFL's original design, updates to the coverage bitmap are sparse. Edges hashed to seemingly random locations across a large array. After execution, the fuzzer scans the entire bitmap to reset, classify, and compare it. This means the large portions of memory are repeatedly accessed even though most entries contain zeros. This causes significant cache pollution. The processor loads cache lines that contain mostly unused data. These unnecessary memory operations push useful data out of the cache and increase memory bandwidth usage. As the bitmap grows larger, the problem becomes worse. Now consider BigMap. BigMap introduces one additional lookup into the index bitmap during edge updates. At first glance, this might seem like a little extra overhead. However, this lookup is highly predictable and often hits in the cache. More importantly, the expensive operations like reset, classify, compare, and hashing now only operate on the dense coverage region. Because this region is compact and contiguous, it exhibits strong spatial locality. The memory accesses are sequential and predictable. It also exhibits temporal locality since the same coverage entries are frequently reused across executions. As a result, BigMap significantly reduces cache misses and memory traffic. The key trade off is simple. BigMap performs one extra memory access per edge during updates. In exchange, it avoids scanning megabytes of unused memory per test case. This trade off is overwhelmingly beneficial. Most importantly, the runtime of bitmap operations now depends on the number of active edges rather than the total bitmap size. This breaks the direct link between map size and performance, and that's why BigMap can support very large maps without suffering throughput collapse. So far, everything we've discussed has been conceptual and architectural, but the real question is whether this redesign actually delivers measurable improvements in practice. So let's turn to the experimental results. Now that we understand the design and why it should improve performance, let's examine the experimental results. First, the authors compared throughput as the bitmap size increases. With a default 64 kilobyte map, both AFL and BigMap perform similarly. However, as the map increases sizes to 256 kilobytes, 2 megabytes, and 8 megabytes, the difference becomes dramatic. AFL's throughput drops sharply as the map grows larger. At 8 megabytes, AFL slows down by more than 30 times compared to its default configuration. In contrast, BigMap's throughput remains almost flat across map sizes. At 2 megabytes, BigMap achieves about 4.5 times higher throughput than AFL. At 8 megabytes, it achieves around 33 times higher throughput. This confirms the central claim of the paper. BigMap decouples performance from bitmap size. Now, let's look at the scalability results shown in this figure. On the top left, we see BigMap's normalized throughput as the number of fuzzing instances increases. The black line represents ideal linear scaling. The red line represents the average performance across benchmarks. We can see that BigMap scales reasonably close to linear as we increase from 1 to 12 fuzzing instances. On the top right, we see AFL scaling behavior under the same conditions. Here, performance quickly plateaus and even declines as more instances are added. This happens because large bitmaps cause significant cache contention when multiple fuzzers run in parallel. BigMap avoids much of this contention by operating only on the compact active region. The bottom graph shows the speedup of BigMap over AFL across benchmarks. As we increase the number of instances from 1 to 12, the performance advantage of BigMap grows. With 12 instances, BigMap achieves around 9 times higher throughput on average compared to AFL. In addition to throughput improvements, the authors also measured crash discovery. They found that BigMap uncovers approximately 33 to 37% more unique crashes when larger maps are used. This demonstrates that reducing collisions and improving efficiency directly translates into improved bug discovery. Overall, the experimental results strongly support the claim that BigMap enables large coverage maps without sacrificing speed, and even improves scalability in multi-core environments. So, beyond performance improvements, what does this mean for the future of fuzzing research? To conclude, this paper addresses a subtle but fundamental limitation in coverage-guided fuzzing. Hash collisions in fixed-size coverage maps reduce the fuzzer's ability to distinguish new program behavior. As software systems grow larger and coverage metrics become more expensive, this problem becomes more severe. In addition, a natural solution is to increase the bitmap size. However, naively enlarging the map introduces severe performance overhead, causing throughput to collapse. BigMap challenges the assumption that large coverage maps must be slow. The authors show that the true bottleneck is not the map size itself, but operating on unused regions of the map. By introducing a two-level bitmap structure, BigMap stores coverage data compactly and performs expensive operations only on active entries. This redesign decouples runtime from total bitmap size. As a result, fuzzers can use large maps more efficiently, reduce collisions, and scale better across multiple cores, and discover more unique crashes. Beyond performance improvements, BigMap enables researchers to experiment with richer and more expensive coverage metrics without worrying about collision pressure. BigMap does not only optimize fuzzing performance, it fundamentally changes how fuzzers can scale, enabling larger maps, richer coverage metrics, and more aggressive experimentations. It expands the design space of coverage guided fuzzing. Thank you for listening. My name is Benson Bowie, and I thank you all for listening.